Hello and welcome, friends, to class 24 of my quantum mechanics, of my physics 2 class, I should say. We have actually, quantum mechanics is always in the back of my mind, now it comes automatically. We started discussing everything actually with the ideas of quantum mechanics 2, the concept of wave nature of matter, the concept of how do you get the wave function, the approach of Schrodinger, the from Schrodinger's idea, how do you apply that? How do you describe a physical situation like electrons in a metal, electrons in a diode, electrons in a box, 3D box problem I'm talking about. And we have got pertinent connection also. Okay, in nanomaterials, so we studied quantum dots. That is a 3D box problem. So quantum ideas was developed, quantum ideas was applied. They were applied in the various problem, and we studied bit of quantum. We studied quantum computation, which is also the application of quantum mechanics, but with a different viewpoint, as you know now. Okay, with the state vector approach. And when I was talking about quantum mechanics, I told you that most of the problems we discuss are for one particle. When you go for many particle case, then you have to go for average value, etc., etc. Now, uh, when you talk about very large number of particles, like for example, gas molecules moving, lakhs of gas molecules are there, crores of electrons are moving in a metal. So for this purpose, it is not practically possible to solve a Schrodinger equation for every electron in a metal. There are crores of electrons moving. Or even in a semiconductor also, there are a lot of electrons moving together, the majority electrons in maybe in a diode. So you cannot describe the individual particles and describe the problem, which is a very cumbersome and tedious mathematical job. So that's why scientists and physicists actually develop the technique. That is, you develop a technique of describing mechanics of many objects together. So that is a technique of statistical mechanics. Statistics is used for many object cases. So because we are talking about mechanics, the motion of the maybe lakhs of electron, okay, large number of photons maybe. So that's why these mechanics is called statistical mechanics. So the idea is that, this is me. For gas molecules, we use classical statistics, but for electrons, we use quantum statistics. For phonons, we use quantum statistics. But for photon and phonon, the idea of Bose and Einstein will be used. Bose-Hessian Bose. And for electron, proton, neutron, idea of Fermi will be used. So statistical mechanical approaches do differ slightly. So that is something I told you. For gas molecules, we can container at a given temperature with some energy 3/2 kT randomly in a container. That description can be made with Maxwell-Boltzmann statistics or classical statistics. So in classical statistics, very important and vital concept of quantum mechanics, like say quantum number, like the concept of electron spin, the concept of Pauli's exclusion principle, that they do not never come because it's a classical idea. So the word spin is very important when you talk about statistical mechanics, is quantum mechanics. So spin is an intrinsic motion, is intrinsic property of the electron. Spin is connected with magnetic property, because if electron moves, you can see, depending on the direction of the rotation of the electron, you will be developing magnetic field. Okay, so you will be developing magnetic field. Okay, depending on the direction of the motion, so you'll get it. Okay, either spin up or spin down depending on the direction of the magnetic field. Spin may be up, spin may be down, spin may be intermediate, as you know from the from class quantum computation. Now for electron, proton, neutron, just like as you can see there, in metals electrons are moving, crores of electrons are there, all moving randomly. That is called free electron theory, which you studied in Root's model. So electrons move randomly. Okay, fine, they're large in number. Okay, but you see the problem is that electrons obey Pauli's exclusion principle. Electrons have got some defined spin. They are in spin will be half. Every electron spin is half h cut. Plus minus, plus half h cut means up, minus half h cut means down. That means direction of the magnetic moment. So for electron, proton, neutron, they are called fermions. Their spin is half h cat or integral multiple. Suppose 3 by 2 h odd multiple of half h cat, that is half h cat, 3 half h cat, 5 half h cat, like that. Okay. So this type of thing, particles are called fermions because they obey the idea of Pauli, of Fermi. So Fermi-Dirac statistics is valid for electrons. All electrons look very similar. So they are identical particle. You cannot differentiate electron 1 with electron 100. If you've got 100 electrons are there, all move in a similar way. So that's why for these cases, okay, Fermi-Dirac statistics, we will be using the, okay, fine, the electrons are obeying fermions. So how what is the prescription of Fermi statistics? We have already discussed. I will again remind you. But here the specialty is that electrons have got are defined with their magnetic property, spin. Okay, and Pauli's exclusion principle is also valid, as you know. Photons, you can see they obey the idea of Bose and Einstein, and for photons, there is no Pauli's exclusion principle. So what Pauli's exclusion principle tells, you cannot keep two identical electrons in the same energy level. Okay, you can keep them with same energy, etc., etc. You cannot keep two similar electrons in this, or two similar particles in the same energy level. For Bose-Einstein statistics, there is no restriction. No Pauli's exclusion principle. Example of particles who obey Bose-Einstein statistics are photon, light, a piece of light, photon. Okay, so these are all photons. You can see in the picture, those yellow dots are all photons, but all of them are looking similarly. So that is the beauty of symmetry. And another point is that, you see, if you look at the idea, you see, so all the photons are similar. So all of them are photons. So they are identical and they are indistinguishable. Same thing happens in a metal for electrons. All the electrons are similar, so identical and indistinguishable. So you cannot change them. You cannot alter them. But the problem of the electron is that electrons obey half integral or odd half integral, electron, proton, neutron. Now the spin of the of the electron. So on the contrary, in case of photon or phonon, the spin magnetic moment will be either 0 or integral spin. Okay, that is 0, 1, 2, 3. This integral spin. Okay, half h card, 2h card, like that. This is the bosonic nature of the radiation. So the particles who obey Bose-Einstein's idea, they are called bosonic particle. Okay, they are called bosonic particle. Okay, so this is a prescription of the Bose-Einstein statistics, that all the particles are very similar, identical, and indistinguishable. You cannot distinguish them. Next point is that all the particles, okay, have got zero or integral spin. They do not have a Pauli's exclusion principle. So these are the ideas of the differences between the three statistics I told you earlier also. Today I reminded you. Herein, concept of phase space comes in. The space we are living here is called Cartesian space or position space. Macrostate and microstate concept I already shared earlier lecture notes. You can see macrostate means the property as you see, the overall property, not the microscopic detail. Like what is the velocity, what is the temperature of that container, with okay, all these essential information, okay, that you can arrive at. Those all those essential information you can get. And macrostate is the actually overall description. What is the volume of that container? What is the temperature of the container? What is the energy of the particle? Okay, there is a arrangement. So if you are asked to calculate, to describe this system, you can compare the classical statistics, a classical statistics problem or Maxwell-Boltzmann statistics problem. Okay, so what would happen? Because it is an application of Maxwell-Boltzmann statistics, so what would happen? That you can now separately describe them. Okay, what would be the velocity distribution of the particles moving here, okay, in a container or something like that. You can see there the total description of the system is the macro state. That is what is the volume, what is the temperature, what is the pressure. So in macro state you describe all the objects together, and micro state means individualistic description of the each of the object. Okay, what is the momentum, what is the kinetic energy, what is the position. All these individual data can be obtained from the micro state. I have shown some cases of macrostate and microstate calculation, two particles, two energy states. So if you follow the Maxwell-Boltzmann statistics, these are the probable cases, as you can see on the screen. So macrostate is 2, because one option is that you keep both of them in 1, remaining 3 in 2. So automatically two options are created, and for the A and B are the basically intensity values. Okay, intensity values. So how they will be distributed, that information is stored here. Now, if you do the Fermi-Dirac statistics, what would happen? For the Fermi-Dirac statistics, number of what is the message? These are the, suppose again two objects are there, two objects, two energy levels. Okay, so particle distribution may be like this. Okay, because if it is Fermi-Dirac statistics, number of particles in an energy level is only one. Okay, it is allowed. So it is like that. Many particles to single particle. So in single particle case, what you notice that you are not describing all the balls together. You are describing them individually. Okay. So Fermi-Dirac statistics tells us in an energy level there will be this one electron with that way. Okay, in the same one. So they obey Pauli's exclusion principle. This is the effect of they obey Pauli's exclusion principle, as you can see there. Okay, number of electrons in an energy levels are all one. Okay, so macrostate 1, microstate 1. Now both Einstein way of thinking. All the particles are the similar, so all are A's. Okay, all are red balls. So it might happen both the balls are in the state 2, both the balls are in the state in the next case. In the next case, you see again both the balls are in the lower energy state. Okay, so this is the way you can describe it. Okay. In general, you can extend your discussion for any case. Okay, any large number of particles also you do it. In this case, three particles in three energy state. Now, same problem as I have presented to earlier also, only all particles are identical, so B will be A. And this is Fermi-Dirac statistics, again all particles are identical, A will be A, and you cannot keep two fermion in the same energy level, so that Fermi energy in the same energy level. Okay, the Fermi-Dirac state I have told you. Even you can use the formula also. Now this is a concept of Fermi-Dirac statistics, it has been already told. This is the way the particles do occupy. Lowest energy state is most configurable and most preferable. Higher energy states are not. Now next question is that how to reach. Okay. So what you can do, I give an example to you. Okay. Example is that so far we have been keeping two particles in one particle in one energy level. So if I've got 20 particles in 20 energy levels, I can keep them. That is a prescription coming. Okay, told 20 particles means you have to keep 20 energy. That is, if with their electron, one per energy level. Okay, but this is not the scientific way we have been proposing. You have to get a scientific way of how okay, there will be particles will be occupying from low energy state to high energy level. Okay. Now you see how large number of particles will be distributed in large number of energy levels. This law is actually predicted according to the laws of statistics. This is given separately. Okay. So if you have got large number of electrons moving also, so whatever they are telling, these are all not coming. Okay, now particles are occupying one particle in each energy level. Okay, you can see there one particle in one energy level. But how do you adjust it? Okay, if you have got crores of electrons occupying say crores of energy level, for that purpose one distribution function is there that tells how particles will be going from low energy state to higher energy state. Okay, there is no rule. What would be the number of particles in energy level? Just like because they don't obey Pauli's exclusion principle. Okay. Now that is a Fermi's distribution function. I have discussed a lot in my last video lecture. You can go through that. Here EF is the key called Fermi energy, up to which electrons. Okay. EF is the Fermi energy, as you can see. So Fermi energy level is defined as energy level up to which electrons are present in a metal. Okay. So what I did that day, I have shown you this entire Fermi Dirac distribution function. Okay. It's only last video lecture you have to see. Okay, this is the Fermi Dirac distribution function and the plot. Plot we discussed last day. A Fermi Dirac distribution function, four options are there. F is 1 by 1 plus exponential. Okay, you can say I've discussed it. Okay, how those curves are generated at t goes to 0, t greater than 0. You can see there those blue and orange. So main difference that has come up, as I told you earlier also, by this time you realize the particles are very similar, identical and indistinguishable. Okay, and the spin for fermions are like okay, it is defined the in half odd integral spin, and for bosons it will be only integral spin. Okay, the difference is that in classical statistics all particles are identical, but you can distinguish them. Suppose I've got five balls, red, green, blue, yellow, like that. So basically, there I am discussing about all balls. All are identical objects, but the distinguishable objects. Okay, and that facility is absent in the case of photons. Okay, it is only applicable for electrons, and obviously Einsteinian idea also, as you know by this time. sorry, Fermi-Dirac idea that tells us how particles will be going to variety of energy levels. Okay. So these are the differences that you can see here. Main problem is in this concept of spin, electron spin, if it is zero or odd half integral multiple spin. So we can now show you. This is the Fermi-Dirac distribution function. Its temperature dependence also you have shown. Okay. So now, what is the message? At absolute zero, if you plot it, the probability of occupancy against the energy. Okay. If you plot distribution function, it looks like this. Okay. Here it is 1 and it goes to 0. Okay, here it is also 0. This is the Fermi-Dirac distribution function. Now if you vary the temperature to t greater than 0, the same distribution function changes like this. Okay, so this is something funny. So what I shall do now, so you see at absolute zero and or even particularly all the energy levels, see these are the energy levels. These are the various levels of energy. So this is the energy level. Okay. What do you notice here? How the particles will be occupying this energy level, that story is mentioned there. Okay, by that formula it will occupy. And you see what you will notice, if this is your Fermi level, all the energy levels below Fermi level are there. Okay, so Fermi level is the energy level below which all the electrons are present. So electrons are present here, and above which, okay, it goes to zero. Now what shall I do now? Let me show you how it varies from semiconductor to semiconductor. Suppose I have got a suppose we differentiate between metal, insulator, and semiconductor. Now if I plot it, suppose this is my, I am considering flat band. This is the bottom of the conduction band, and this is overlapping with the top of the valence band. Okay. Here, this is the top of the valence band. Okay, this is the valence band, top of VV, and below that Okay, is here I am getting into that. Now the concept is that if you keep the system at absolute zero, okay, because of this distribution function, it is one. Okay, all are occupied, and here all are occupied, and here all are unoccupied. So here also below this is the Fermi energy level. Okay, what would happen? That if these are the energy levels plotted in this direction, so all the energy levels are there. Now they will be overlapping. So Fermi level will be in this overlap region only. So Fermi level may stay here within the conduction band because all the electrons are present up to the Fermi level. Now in insulator, top of the valence band and bottom of the conduction band, they are far apart. Okay, like this. So this is a huge band gap. Now this is zero and this is Fermi level. And for semiconductor, this gap is much reduced. The gap is there, so Fermi level will be somewhere here. So in this case also, gap will be there, but Fermi level is somewhere there. So this is a story for metal insulator and semiconductors. Now let us not and semiconductor. Now let us consider what happens in case of doped semiconductor. This is intrinsic semiconductor. Okay, suppose n-type doping. In case of n-type doping, these are the energy levels. Suppose okay. This is the top of VV, top of arrangement. Bottom of conduction band. Now, if you have to make n-type, this is filled in absolute zero. Now, if you do n-type doping, you need an acceptable, it need a donor level here. So its job is to donate the electron to the valence band. Now, what would happen? Okay, so it will be supplying the electrons in the conduction band. Okay, so the idea is that it might happen that this region, okay, somewhere there, okay, in between these two, suppose this is our energy level, like this. So for metal also, you see the EST, okay, you can see this is the n-type semiconductor. So for donor level, there it will be providing adding electron to the conduction band of the system, and more electrons will be now moving to the conduction band. Okay, so you see electrons have moved up as shown by these arrowheads from the donor level to the higher energy level. Now the material that is used for the preparation of electron, for production of this electron, okay, You can see there is. Now similarly, if I do p-type doping, for p-type doping, so this is the bottom of conduction band. P-type means there will be an acceptor level. So what would happen? Here it is going to accept the electron. Okay, this is the acceptor level. It will be accepting the electron. This is the bottom of the conduction band. Okay, now what is the objective? Objective is that if this is the Fermi level, it will be accepting electrons from here. If it accepts electrons from here, so automatically where the Fermi level will go, it is the energy level up to which electrons are present. So it will be somewhere here. It is close to the acceptor level. Okay, now make a PNP suppose I want to make a diode. In case of what you notice, in case of PN diode, this is what you see for N type. This is the valence band. This is the conduction band. Electron. This is the donor level. Okay, Fermi level will be here. So electrons are moving here. Okay. In case of P type, this is acceptor level. These electrons are present up to this level. Now, suppose I wish to make a diode, PN junction. At the Fermi level we go. In case of, so now the moment to make the diode, the junction, so this is the Fermi level. Fermi level of the system is a common. Now suppose P side is the left side, so it will be like this much. For P side means acceptor level will be close to the Fermi level. This is the Fermi level. So this will be the acceptor level. Okay. So this is the valence band, this is the acceptor level, and all these things will be there. On the contrary, for N-type semiconductor, you see it is close to the conduction band. So for N-type semiconductor, it will be like the donor level, to the conduction band, N-type semiconductor. So it is to donate the electrons there. So it is they are moving, remaining here. So Fermi level is there. So what happens? Your band diagram of the diode is now looking like this much. This is the band diagram of a junction diode, as I have marked here. Entire explanation of any semiconductor device will be diode. Suppose how an electron will be now moving from here to there, because this is not the right way of moving. Okay, a lot of energy loss, etc., etc. there. So at that time also we told Okay, that electron, this height is equal to the barrier potential in corresponding energies. So this is the way you can make a diode. Even you can make a transistor also, PNP suppose. You see, common Fermi level for P side, valence band is close to here, and conduction band is here. For N side, opposite story, conduction band is here. Okay. Now this is the donor level, and this is the top of the valence band. You join this, and now N side will be coming again against the valence band is here. Okay, acceptor. There will be one acceptor level also. And ultimately, very similar to this is P side only. So this is, so if you join here, it is like this. So this is the way. Suppose an electron is here. This is like the base region. It can go here also. It can go there also. Okay, two options are there. But before going, you can see. I hope you can the transistor part. Okay, please see. This is the Venn diagram of a PNP transistor, and this is for a diode. So how you see Fermi level is remain common, deterministic. Even if we make the diode also, device also. So basically now device action is how do you create equilibrium across the Fermi level. So these are very interesting idea. That is how it is a level up to which electrons are present, and ultimately showing the action of the diode. So here it was showing how whether electron will be crossing this. This is a problem of one of quantum mechanics. And here also this electron is trapped here almost, how it will go. So these are all problems of quantum mechanics, but they are automatically coming if you use your sense of uh, which statistics they will be moving. Okay. Now just get back to the PPT a bit. So we have discussed it in line by line. So this is the Fermi energy level in case of metal, insulator, and semiconductor. Metal you see all overlap. Insulator, semiconductor in a small gap, insulator large gap. Same story. Okay. Okay, now the same story. Now this is N type and P type. As I've just told you, Fermi level is close to the conduction. Look at the drawing I have made few minutes back. P type also same story. This is the junction diode. This is the band structure of the NP problem. Electron. You see the same thing is discussed now. Now another very important idea is the concept of density of states. Density of states means it is actually basically number of quantum mechanical states per unit energy range. That is called the density of states. I repeat it, density of states means number of states per unit energy range. Okay. That is called the density of states. So now it has got a quantum mechanical origin also. You can see in the picture. Density of states of one dimension. It is like spikes. For two dimension, it is like steps. These are all nanostructures that we studied earlier. For zero dimension, these are all lines. For 3D, it is parabolic. Okay. Okay. So how density of states are distributed in variety of nanostructure that is shown there, as you can see here. It is the number of energy states per unit energy range. Okay, D and D. Actually, according to the studies of quantum mechanics, if I just get back to the picture here, according to the prescription of quantum mechanics, you should know the it tells us, you know, the concept of for a, you see, quantum mechanics star tells me for one energy there is one shell. Same quantum mechanics tells me for same energy there will be more than one shell. So the psi 1, psi 2, psi 3 are degenerate states. So that means with same energy there may be more than one states. So if I have got a energy continuum, I consider many energies together. So obviously, if this is a direct plot of energy, so obviously now I can say with unit energy, okay, due to per unit change of energy, what is the number of density of states, number of energy states I am getting. So we define a term called D and D. N is the number of energy states, and D is basically the D and D is the differential change. Okay, number of energy states per unit energy balance. Okay, this is called density of states, and you can understand for a for the same energy, okay, within the like that for the same energy there will be more than one state because of degenerating. So there are 5 states, for example. So basically, number of states per unit energy range may be more than what you anticipate. More density of states means particles are actually moving. If it is non-zero means it's a good signature. Another important issue, okay, that often comes up is that how does it look like from various types of structures. Now just get it as a shown you also. The density of states for the three-dimensional structure is like a parabola. In two dimension, if you calculate density of states like steps, mm, okay, step potential problem is like a step one in one dimension. It is like spikes. In two zero dimension, it is like this. So it varies. Okay, in narrow structure it becomes important. So now this stops our discussions on density of states. You can see it is calculated in 2D. How it calculated is shown there. You can see there is equal to h cut square k square by 2m. If you calculate d, it is h cut square k dk by m. You can also see here the d is there. So number of energy states per unit range is that area dkx dky, okay, divided by a is the density. Okay, number area So it is m square by pi h cat square, which is constant. Okay, you see that, so you are getting a circle. 3D, same problem, h cat square case. If you take d decay, you get this much, and then d and decay is the number of states per unit volume. So d and d, you can see there, d and decay cancels. So ultimately it is e to the power half. E to the power half means if you plot it in three dimension, it should be parabolic relationship. I hope you are getting my points. Okay. So for a bulk parabola, for a film step, for a quantum or spike, and for a, you see it's always compared to the three-dimensional case, ideal case. Quantum dot is this spike. Same story. So many more things are waiting for you in statistical mechanics. Is a huge branch of physics. Okay, a lot of it's a highly proficient branch. A lot of people are working on it, and the prediction of statistical mechanics has got a role in material science. Okay, in characterizing material, etc. Okay, but your syllabus does not demand more. So here it is stop. So next the honors should be getting into another topic, which is a highly classical topic, that is electromagnetic theory. Okay, thank you for the time. So as you can see now, I just get back to the discussion of density of states. And d and dk is it is basically number of energy states per unit energy range. D and d. So in one dimension, you see the formula of energy, h cat square k square by m. Okay, it's a classical formula. Okay. So if you calculate take d and d, which is L by 2 pi. Okay. So from here on, you can just calculate d and d. Okay. So if you multiply that, you write down that in that way, d and d is equal to d and dk d. So it is like e to the power minus half, which is a you can see here it's parabolic relationship kind of thing, but it's almost like that. Okay, like that spikes. Two-dimensional density of states you can also see there. 2D means okay. Energy is again h cat square k square by 2m. There is a prescription. So again you can take d of e. So d and d, you can see if you see d of e, the number of energies responded energy range is that a into by 2 pi square, all these things you can see dkx dky. So from here on, density of states is that number you divide by a, you get that value. So it's a constant, so you get a circle. Okay. Again, m square by pi h cat square. Okay, it's a constant quantity that you can see there. So you get constant. So that's you have got it like spikes. And you got it like steps. But it can change with m step, the particle mass. Three dimension, same problem, same formula. D decay you calculate, D and D is that much. C to the power half means parabolic. Okay, so get that. So this is how it varies. In 3D bulk material, parabolic to quantum, the one-dimensional films. Okay, it is like steps. Quantum wire, you can see the spikes are there, and quantum dot is there. Quantum wire means one-dimensional quantum nanostructure. You can see like spikes there. Just few minutes back, I told you how we do it. 1D, 2D, 3D nanostructure. This is for 1D, you see it is like spike to the power half relationship. Okay. 2D is this much. 3D is this much. So now if you compare 3D graph is like that, 2D, 1D and vectors are also included a bit in your course. So if you now look at it, it looks like this. Okay, if you compare 3D, 2D, 1D and 0D. So here I have to stop. So we have discussed about various facets of statistical mechanics. It is the most profound uh, branch of theoretical physics. Many new concepts are coming every day, and some old legacy is also there. Okay, so if you're learning physics courses only, okay, so when I stop, so next day, well, but statistical mechanics does not stop. Okay, so next day we'll come out with a very highly classical topic called electromagnetic theory.